Welcome to the lecture 29 of Physics 10 in 30 lectures. We wrap up this week on nuclear and particle physics with this lecture. Having covered nuclear fission in the last lecture, we continue with the considerations that go into nuclear fusion, again using borrowed Physics 4C lecture videos. And we begin to cover physics of elementary particles, with the story of discovery of neutrino in beta decays. More of a hypothesis initially, and a couple decades later directly detected. And we introduce additional quantum numbers that are conserved, especially the baryon number and the lepton number. And the idea of antiparticles introduced by PAM Dirac, which helps with conservation of these new quantum numbers. Unfortunately, this is as much time for particle physics as we have this week. We will pick up the remainder of what is essentially optional particle physics topics in our final lecture set, lecture 30, next week. The remaining sections in this lecture set covers number questions from chapter 14 homework, and in additional particle physics section, we look at a couple conceptual homework questions dealing with particle physics concepts that I have not yet mentioned in lectures, although, as always, covered in the textbook. And in the same lecture, I also demonstrate, for those who may be interested, how to find additional particle physics lecture videos from Physics 4C. These topics are covered mostly conceptually, and I believe they are accessible to every student in Physics 10. That's all for this week. We will wrap up our coverage of particle physics next week with lecture 30 as we prepare for the last set of timed assessments. Here in this lecture set, we now continue with nuclear fusion. When we are talking about nuclear fusion, we are, in some sense, talking of an opposite process from fission. So as we are considering nuclear fusion, I do think it is good to contrast it with the nuclear fission that you have seen. In the case of fission, the kind of reaction that you have seen is, well, fission or a separation of a heavy atomic nucleus. So the example that you see in the textbook and in the lecture is the fission of uranium 235 isotope. The kind of the structure of the atomic nucleus that allows a fission occur, it's quite specific to a particular isotope. So take uranium, for example. Uranium-235 is fissile, it undergoes a fission. And uranium-238, it's not fissile. And at least at our level of covering this, I'm not going to give you an explanation why one is a fissile and one is not. But this is the process that occurs in fission. And one of the things that tells you that fission is a kind of a process that can happen is when you look at the atomic masses. So you look at the combined mass of the neutron and uranium-235. That'll give you the rest energy that you're starting with. And you look at the potential decay product of the daughter nuclei, then you will see that the final rest energy here, it's less than the rest energy that you're starting out with. So from that rough high level 30,000 feet view, you can see that when you have a neutron plus this heavy atomic nucleus, that it's more energetically favorable for this to split into smaller, lighter nuclei. So and the details of the process that occurs, that's the part that I'm saying. It kind of depends on the particular isotope. We are not going to go too much into that detail. But at this, again, 30,000 feet view, you can see that it, just looking at rough numbers, that the process that occurs from the left-hand side to the right-hand side is energetically favorable. And in our previous discussion about fission, we ended at talking about how this is a kind of a stimulated process, that this is activated by collision of neutron with a fissile material. And in fact, controlling fission reaction has a lot with controlling the neutron economy. So I guess the best way to phrase that in a way that's not misleading is controlled through neutrons. I'll just say neutrons. And in fact, you see that aspect of that when you read about nuclear reactors. So in nuclear reactors, you have something called moderators. And I think moderators are something that you don't have in a nuclear bomb. But in a peaceful nuclear reactor, you have something called a moderator, and the role of moderators are really to control the neutrons. The neutrons so in the fission reaction produces their own neutrons, and these neutrons that come out of these reactions are generally high energy neutrons, and high energy neutrons are less likely to react with another fissile material to produce a fission reaction. So the role of moderator is to actually slow down these neutrons, make the reaction more likely to happen. And I think way back in, is it 2013, with the last well-publicized nuclear disaster in Fukushima, one of the things that you might have heard about was the water in the nuclear reactor. The water in the nuclear reactors in some designs, serve a dual role as the neutron moderators, which facilitate these nuclear fission reactions to occur, and also as a coolant. And at some point when the pumps weren't working because the electricity was out and water wasn't circulating and all of that. So that's a fission. Those are the details that we consider when we are thinking about fission. And when we are thinking of nuclear fusion, the kind of the details that we are concerned with, it actually changes quite a bit. The things that we worry about when we were thinking about fission, a lot of that kind of doesn't matter anymore, and new considerations come into place. Because in trying to get fission reaction to happen, a lot of that actually really deals with the neutrons. That's the key number one thing that you think through. Whether a material is fissile or not, it really has to do hey, how many neutrons does it produce in this reaction that it splits it apart? If it produces too few neutrons, then it's not fissile. If it produces enough neutrons, then it is fissile. With a nuclear fusion reaction, that doesn't quite, it's not the primary concern. And so the nuclear fusion reaction is kind of what it sounds like at the fundamental level. It involves nuclei, or the atomic nucleus, fusing, coming together and becoming heavier isotope. And as you think this through, I think you will see that there has to be more steps involved here, because imagine the simplest possible fusion process. So the simplest possible fusion process would be a hydrogen fusing with another hydrogen, and then turning into what? Helium-2. That hopefully, if you are paying attention through this chapter 10, that's not quite right, because helium-2 is not one of the isotopes of the helium that you are familiar with. You have heard of helium-3 and you have heard of helium-4, but helium-2 is not. It's not one of the stable isotopes of helium. And in fact, one of the things that you have seen leading up to here is the island of nuclear stability. So just to briefly sketch the chart, what it looked like was if you plot for every stable or long enough lived isotopes, if you plot the number of neutrons and number of protons, the kind of the stable isotopes, they more or less follow a straight line until you get to the more heavier nuclei where there are more neutrons than protons. So if you are thinking of forming these heavier isotopes here from these lighter isotopes here, then starting with the hydrogen, which only has a proton, at some point you have to turn some of these protons into neutrons. And so this is the more detailed portion of the process that I wouldn't trust myself to remember, mainly because I'm not an astrophysicist and I don't think about these particular processes too often. But your textbook does mention this in the portion where it talks about the nuclear fusion reactions that take place in the sun. That's the what they call the proton-proton chain. And this is describing how, starting with hydrogen, the most common, most abundant building block in the building block of normal matter in the universe, you would get to the next heavier isotope, to helium. So it's describing this chain, proton, proton. It forms this, and I guess, yeah, helium-2 never really forms. So in this process, one of the protons become a neutron, forming a deuterium. And as the one of the proton becomes a neutron, charge is conserved, so it produces an not electron, produces a positron, and it produces this one more particle that we are actually a week early to talk about, neutrino, which I kind of hinted at the very last lecture in this chapter, but we will save the introduction of neutrino until next week. But it does that. And this positron, it'll annihilate with electron within the sun and go away, turn into gamma rays. All of that is for next week. We haven't started talking about antiparticles yet. But so hydrogen plus hydrogen becomes deuterium plus some other things. And hydrogen plus deuterium now becomes helium-3. And helium-3 is not the most common isotope of helium when you look into the sun. So this helium-3 and helium-3 combines and becomes a helium-4 plus some spare protons, and these will go through this proton-proton chain to make more helium-4. And all this process is basically adding up to how this is describing how hydrogen is fused into helium in the sun or any star that we imagine. Sun is the nearest star that we know, and it's the most closely studied star. And we think, based on astronomical observation, this is the primary process that occurs in all the stars, all the new stars. And as you are thinking about this process, there are really the two biggest thing to consider, which are the barriers that need to be overcome. So one is, so far we've been drawing diagrams, but I want you to really remember that when we describe hydrogen, or technically proton, in these interactions, we are talking about two positive charges that somehow have to come near each other to the point where nuclear forces become appreciable. And as we will talk in detail next week, nuclear force is a short-range force. The strong nuclear force, it has somewhere around the range of 10 to minus 15 meter. That's about the size of the atomic nucleus. Outside of that, it starts to become negligible. So these two protons have to come 10 to the minus 15 meter of each other before the nuclear forces can take over the electromagnetic force that governs most of the other interactions that we are familiar with. And what I want you to consider and realize is that these are both the positive charges. It's just the way things are arranged that both of the particles that would participate in this nuclear reaction, they both happen to have positive charges. And, and until they come close enough to the range where nuclear force can take over, these two positive charges are actually experiencing Coulomb repulsion. So if you had two protons simply near each other, the most common tendency is for them to simply repel each other and be as far away from each other as they can, and no nuclear fission reaction occurs. So there has to be something in the setup that overcomes this Coulomb repulsion. And that leads to the first of the considerations that is necessary for nuclear fission to occur. And what it is, so just leading from here, for nuclear fission to occur, the fusion fuel, which in this case is hydrogen, but it can be other material too, the fusion fuel needs to have high kinetic energy. Because you can almost think of this classically. You can think of these as two positive charges that are moving towards each other. You need to get them to close enough distance where nuclear reaction can take over and allow fusion to occur. And so as they come close to each other, they're going to slow down. And for them to come close enough before they are turned around and repelled back, for them to come close enough, they have to start out with a high enough kinetic energy so that before the classical turning point, they are close enough so that fusion can occur. And in the more high kinetic energy, if you are looking at those each individual microscopic interactions, or from the macroscopic perspective, you would say they need to have high temperature. So that's one of the conditions that needed to be. And as you continue to look at this reaction carefully, what I think you will see is that this reaction describes a fairly unlikely set of circumstances. So for the proton chain that's occurring in the sun, definitely. And we can actually cheat, or we can help it along by for example, providing deuterium. So if you are trying to set up the artificial conditions to make the fusion more likely to occur, nothing says that you have to start out with the hydrogen. You can get heavy water. You can separate deuterium, or I guess heavy water already contains the deuterium. So you can actually start out with the deuterium, or actually hydrogen has a even heavier isotope, tritium, that's actually fairly stable. So you can even get tritium and start out with some tritium to help this reaction along. So that is possible. And even in that case, what you're looking at is a fairly unlikely or rare set of circumstances, because this always involves repulsion. So if they happen to be coming toward each other with the wrong velocities, as in they're slightly missing each other, then it's quite easy for them to not come as close as they can, kind of miss each other. So there's quite of a set of circumstances that needed to happen right. You could say that the processes that are described here, they are on the whole fairly rare processes, especially after the first step, because this can't be just a hydrogen colliding with any other hydrogen lying around. It has to be colliding one of the deuterium. And here you have to find one of the helium-3 that's already formed, make the collide with another helium-3 that's also formed. And so all these are beginning to describe processes that are rare, or at least on the rarer side. And if you need, so this is a phrase that you will see me say sometime next week, which is, it's a saying in particle physics. it's saying whatever is not forbidden is mandatory. And it's a reference to the fact that all the rare things that could happen in particle physics, you actually do see them happen all the time. And the way we make those rare processes happen, we kind of guarantee that they happen, is we have a large number of them. We have a large number of incidences, large number of collisions, large quantity of data. Then within that large set, even the rare processes are guaranteed to happen sometimes. And really what you need is that these things happen often enough. And in terms of kind of material conditions, what you need is for the, let me call it less common collision processes to occur, the fusion field needs to be at high density. So these two factors are what's needed for fusion process to occur: high temperature and high density. And this is the kind of condition that's actually met in the core of a star like our sun. And in fact, that's the success of our solar model that describes the nuclear fusion that powers our sun. It keeps the sun in hydrostatic equilibrium. The energy that the sun produces, it's no longer coming from gravitational collapse. It's coming from the energy released in this fusion process. And I think with some sense of scale for how large the sun is, how much mass there is, I think it's easy enough to imagine that in the core that it would be at high enough density, that the hydrogen atoms that are in the core are so packed together that it's a much higher density than anything else we have on the Earth now. And I think even high temperature part is kind of easy to imagine, sometimes kind of through the wrong process. But I think what's important is that this is something that happens. Now, it's one thing to understand the nuclear processes in the sun, which is, it's an accomplishment of its own. And this is something that really helped us understand astrophysics and actually through the solution of what used to be called the solar neutrino problem, it helped us add to our understanding of the particle physics as well, because it helped us understand the neutrino, the particle we are introducing next week. So there's that. That's one thing. It's something that happens in nature, and we have a theory that describes. That's great. And maybe in another comparison to nuclear fission, what we are describing in the nuclear fission, at least most of the time, this is not something that just happens in nature, or it doesn't really happen in nature, at least not anymore. I think there are some locations on Earth that used to be natural nuclear reactor, not around anymore. This process like this is not something that happens in nature these days. This is a device that we built. And so far in our description of fusion, we are simply describing something that just happens. We don't, this is not a process that we are driving. So one of the kind of goal or technology that's been always 20 years away has been generation of energy through nuclear fusion. And in one sense, that's right. I think your textbook mentions it somewhere. It should talk about fusion reactor. So fusion chain believed to be most practical for using a nuclear fusion reactor. And here, we are kind of cheating, start out with the deuterium instead of hydrogen, so that we have a shorter chain. And people have been doing research on devices like this. I think ITER is the name of the collaboration that does work on this. This is a kind of a confinement thing. And the goal of a device like this is really to produce these conditions in a controllable manner. they need to put together these light isotopes where fusion is more energetically favorable to occur. We need to put them at high temperature, at high enough density, so that fusion occurs. And the challenge here is that no physical material can be used to actually confine the material, because these temperatures are so high that any potential container would just melt. So they use electromagnetic trap. I think they talk about something about very difficult problem, high temperatures are needed. Example, yeah. Yeah, so they're not going into detail. The kind of confinement that um, so they use magnetic fields because fields can withstand any temperature. Um, and the short story here is that a lot of work is still being done. There's work being done at National Ignition Facility. I think that's at Lawrence Livermore Laboratory, that they do fusion research there, and they can cause a fusion to occur. The problem is that it takes more energy to cause the fusion reaction to occur. Compared to the amount of energy they get out of the fusion reaction, they put in more energy. So it's not actually on net producing any energy. Now, there's one way in which we have been able to harness this fusion reaction in a practical way. And this is kind of the story of technology, which is the first place where they get used is for it's for war, because in fact a lot of the fission research was driven by the need during the World War II. And a lot of the funding for the nuclear fusion research has come through the time of Cold War, when United States was competing with the Soviet Union on who's going to build the biggest bomb. And that's what this section is describing. That so the fission bomb, the atomic bomb, has a limit to how much of an yield you can get, because as you heard me describe in the lecture on the nuclear fission, it's about bringing two subcritical masses together quickly to make a critical mass, and then the critical mass then blows up. So there's a kind of actual physical limit to how big of a pieces that you can bring together and then have a bomb go off. So if you are only relying on nuclear fission, there's a maximum amount of explosive power that you will reach. And at some point, the scientists who are working on the atomic bomb realized that using the explosive release of energy of the fission bomb, they can actually achieve these conditions and in a very short time scale. And by achieving these conditions in a very short time scale in a fusion fuel, they can actually ignite fusion reaction. And that's what's called a hydrogen bomb. So it's called a hydrogen bomb because the hydrogen bombs contain fission bomb in it, and the fission reaction is used to trigger the fusion component of it. And once you trigger the fusion component, then the it's a kind of it's a self-sustaining reaction, at least until it burns through the deuterium and tritium fuel that's within the bomb. So for those of you more interested in reading about it, I will just say point you to one scientist. So Robert Oppenheimer was the project lead of the Manhattan Project that produced the fission bomb. And with a lot of physicists who worked on the atomic bomb, he really regretted working on that weapon of mass destruction. And Oppenheimer, Einstein, maybe Feynman, they all later on really regretted working on the A bomb, and I don't think he really worked on the hydrogen bomb for that reason. A lot of these physicists, them working on that weapon of mass destruction, it's during the World War II, they were fighting the literal Nazis, and it's kind of lesser of two evils still. There's one physicist who was central in the development of the hydrogen bomb, who wasn't Robert Oppenheimer, is Edward Teller. Yeah, Edward Teller is, I think he is the father of the hydrogen bomb. Yeah, so I think Teller was actually enthusiastic about working on the bomb, and Wheeler had his contributions, which is what I'm remembering. And yeah, it's thing. Yeah, hydrogen bomb. And okay, I think I was somehow mixing up Edward Teller with John Wheeler, and I think so. I think the story here is it's good to read through, particularly what Wikipedia is calling Oppenheimer controversy. And I would just say, physicists are human beings. They have their shortcomings, and there are a lot of physicists who are working for Nazis, not in US, but a lot of German physicists were working for the Nazis, and it's just good to keep in mind that scientists are not perfect. But hydrogen bomb, that's the only practical use of the fusion reaction that mankind or humankind has been able to control, and that's, I think, where we'll leave things off at.
So as we start talking about particle physics, this is a resource that I want to point out to you. It's a website of the particle data group at Lawrence Berkeley Laboratory, or pdg.lbl.gov. And the reason I want you to point out this source to you is they published a review of particle physics, and I have two of their publications here. Booklet, which is the condensed version, the latest one, and one that's about 4 years old. And this is the unabridged, the complete version they publish, I think, every 2 years. Let me just have this sent around, and I'm going to sound like an infomercial host for a little bit. How much do you think this costs?
Well, you said it was free, right?
$10? How much do you think that booklet cost? $10? Yeah, it's because they're completely free, and that's the only organization that would print it for them for free. So this is a completely free resource, even the printed versions. So you are used to PDFs being free. Like PDFs are free a lot of places. So they actually publish this on a regular basis, and when it gets published, they mail it to you for free. And I guess the idea is that they don't want people abusing it. But like the only people who would use it are people who are interested in particle physics. And it's a small enough community that they are, at least the last 2 times if you ever have to pay, let me know. So they call it order, probably to discourage people who are doing this, spammers. But when you order it, you will see that, I don't know, can I log in with mine? Don't know what address I used. Maybe. I don't know. Oh, let me just try one thing. Maybe I switched it to my regular email address. Okay. So when you order it, you will find that, at least last 2 times I did it, I didn't have to pay anything. So I assume it's still the same. So you create an account, you order it for free, and they don't ship it to you that quickly, but it eventually gets shipped to you for free. So I just want you to highlight it because I'm pretty sure they don't tell you anywhere on the website that it's free, because they don't want people abusing it. But what I will tell you is that this is the best resource for particle physics, both in terms of the quality, because this is the standard reference for people work. They keep it updated because it's a standard reference. They compile all the published data and sort of publish one figure with the error bars. That's the established value for particle masses and whatnot. And they also send you hard copies for free, hoping that it'll be not too many people. So it used to be like like American, one of the APS journals that used to do it, but I guess they started not doing it for free anymore. That's why it's now Chinese physics review that does it. Yeah. So anyways, so I wanted to point out that resource, for those of you who are interested in particle physics, because this is the best resource out there. That handbook is one of the best resources out there, because if you need any of the particle masses, you just look that up there. So with that, let me start talking about particle physics. So what we are going to talk about now is mostly covered in this note. So really the place I want to start out from is this statement, that we are interested in what we are going to call elementary particles, or fundamental particles, or, well, the most basic unit of matter and other things that we don't call matter. But it's just the very basic building blocks of universe are what we are interested in. And what you will find is that once that you are starting point, you'll find that many of the things that you are used to thinking of as being elementary are not actually elementary. For example, elements are not elementary enough for particle physicists. As in atoms, they are not elementary enough for particle physicists because atoms are made up of nucleus and electron. The moment you can say that, it's made up of something, that's saying, oh, that's not elementary. It's made up of some smaller things. So really, these elementary particles will be subatomic particles. And you know two of these elementary particles already. So those two are, let me just start listing them. You know photon. Photon is one of these elementary particles. And you know electron. That's the other elementary particle that you already know. And you don't actually, we haven't gone over any of the other elementary particles yet. So when you look at your textbook will just throw this at you in section 1, Introduction to Particle Physics, and they will throw this at you. And what this is a summary of what's in one of these posters. It's in this poster here. And when you just look at that, the only two particles you know that are here are electron and photon. And it's, I feel that's just too much information all at once. So I wanted to slowly ease you into all the particles that people discovered in the 30s, 40s, 50s, 60s, 70s. I think that's the last time the top quark was discovered or finally confirmed in lab. Oh, and wait, this doesn't have a Higgs boson is not in this list. So if you include the Higgs boson, that was discovered in 2014. Yeah.
There's two called weak force?
W boson. We'll get to that. There's W boson and Z boson, which were produced in the 70s or something, 60s. So maybe I should move away from there. All right, let's keep moving back to here. So two particles, we are going to pretend that they are elementary for us for now, because these are particles you know, and until we get to talking about hadrons or particles produced via nuclear force, strong force, this will be good enough for us. They are elementary enough for us. They will be protons and neutrons that you have heard about, right? And the big spoiler that I have revealed right now is that protons and neutrons are not really elementary. They are made up of even smaller particles, but we can actually pretend that they are elementary because the particles they are supposed to be made up of, quarks, we have never seen a free quark. So, but let's just pretend that they are elementary for now. So this is, if you are a particle physicist living in the 20s and 30s, 1920s and 30s, this was your world. These were all the particles that you know. And your kind of starting assumption is that everything else are made up of these. All the atoms are made up of protons, neutrons, and electrons. All the interactions that you see, it's a result of a photon, electromagnetic interaction. But I guess you do have one hint of that this is not everything that's out there. It's what we were talking about on Tuesday. When you look at the atomic nucleus, if you're only dealing with electromagnetic force, there's no way that atomic nucleus can exist, right? That seems, rings a bell for everyone? Okay. Because in an atomic nucleus, these are the only things you have. Protons would repel each other. Something is binding them together. So there's some other force that's not electromagnetic force that's bonding the nucleus together. And just like electromagnetic force leads to a photon, there would be other particles that are that needed to be associated with that nuclear force. So that's something on the horizon that's going to come up. And in connection to that, I need to introduce this particular phrase or concept. It's the concept of force mediator. Or sometimes it might be called mediator boson, because they all happen to be bosons. And this is kind of why I introduced the Feynman diagram. Because the Feynman diagram, the way it's drawn, it always includes this force mediator. For example, imagine this interaction. Imagine the interaction between a proton and an electron around it, like in a hydrogen atom. Right? Now, when you look at the picture, the way we are used to handling it, do you see a photon anywhere in, well, sorry, so it's going to be an electron cloud, not in an orbit. When you look at that, do you see any photon in that particular interaction in an electron and the proton that's in the core of the hydrogen atom? We don't see any real photon, right? But in the way we handle it in particle physics, you still illustrate that interaction as being mediated by a virtual photon. So if you are drawing that interaction, you would draw them this way. So one way to illustrate mediator boson, for example, hydrogen atom. You would draw the interaction of the electron with the proton in the hydrogen atom as well. You have a proton come in. You have electron come in, and you need to have electron going out, and you have proton going out, and you just say, well, I'm trying to draw this Feynman diagram thing, so it would need to be vertex here, at the vertex electron coming in, going out, vertex here, proton coming in, proton going out, and these would be connected by a photon. So this is the virtual photon, as your textbook labels it. Or in the language that we want to use that will apply to forces that are not electromagnetic, this will be the force mediator. And just to kind of flash forward to what we are getting to later on, here, all these are force mediators. Or all these bosons are the force mediators. Mediates electromagnetic interaction, strong interaction, weak interaction. So that's a kind of a spoiler of something that's going to come in the future. The fact that we have evidences, hints of forces or interactions that's not electromagnetic means we are going to have additional force mediators soon. But for now, let's just start out with the additional particles that make up matter, additional fermions. So these force mediators, they all happen to be boson. I don't think there's a fundamental law of physics that says they must be bosons. In fact, if you have heard of supersymmetry, the entire idea there is based on the fact that it doesn't have to be that way. And so, but the universe as we know it now, it just happens so that all these particles that make up matter, they are fermions. Or let me just call them matter particles. So what I want to give you a long introduction to is how other matter particles were discovered. Because these are kind of a normal, usual matter particles that you are familiar with. You've seen them since chemistry. And the matter particles that we are going to talk about now are the ones that were discovered either by accident or by people just pondering things in the elementary interactions. So let me start out with the discussion of beta decay, which is what we were talking about last Tuesday. And I asked you to hold then to believe in this fiction that in a beta decay, this was all we had. So this is the fiction that we were looking at last time. So what's a beta decay? Like what phenomenon or interaction are we referring to in a beta decay? Yeah, so beta rays are electrons. So beta decay is a nuclear interaction which ends up with a process that ends up with the emission of an electron, right? And the particular process that we are looking at was where a tritium, hydrogen 3, goes into helium 3 and emits an electron. That's what we looked at last time, right? And now that we are talking about elementary particles, let me give you an even more elementary version of it. It's not as easy to set up an experiment for reasons that I'll explain. But what this is, let me represent it in a more, in terms of the elementary particles. What this is one proton and two neutrons, right? Going into helium-3, or two protons plus one neutron and an electron. So you have what's sometimes known as spectator particles. Particles that are not really doing anything. That's just there to spectate. So let's get rid of those spectator particles. I have one proton here that, that's apparently not doing anything. And I have one neutron here that's apparently not doing anything either. So get rid of that. So at the very basic elementary level, what you have is one neutron turning into a proton, in the process emitting an electron. Okay? So that's the very elementary representation of what's happening here. Neutron becomes a proton emitting an electron. And if we were to try to draw a Feynman diagram, it might look something like this, which is not going to look like the elementary vertex for electromagnetism because this process is not happening by electromagnetism. There is no electromagnetic process that would turn a particle into another particle. So, but let me just draw a kind of rudimentary version of a Feynman diagram. It would be, I have a neutron coming in. That neutron turns into proton for some reason, and it also emits an electron in the same process. And this is the vertex where all of that's happening. Good? Questions? So this is a new type of interaction, new type of primitive vertex, new type of stuff. So we are not going to hold this to, this must be broken down into electromagnetic primitive vertexes. We don't need to have that because it's an entirely new interaction. But the one rule we want to still hold up is that at this vertex, all conservation laws must hold. Right? And last Tuesday, we actually looked at one consequence of holding to this conservation of energy and momentum. Do people remember that calculation we ended with on Tuesday? So, what was the conclusion we came to looking at decay of tritium into helium-3 and electron?
Like the coil energy can almost be ignored, so all the...
Yeah, that's one. And we calculated on electron energy, right?
Yeah.
So the consequence of holding to conservation of energy momentum is that this is actually a general rule. When you have a single particle that decays into two particles, then these two particles must have definite energy and momentum, right? Because there's no other possibility. But when people were actually doing careful measurements with the beta decay, actually measure the energies of these outgoing electrons, this is what they found. So this is actually a plot of tritium decay that I not borrowed. I'm doing it properly because I actually cite the Catherine collaboration that published it. So this is the plot of the beta energy of tritium decay. So beta energy meaning energy of the electron that's coming out of the beta decay. And this is what they measure. I mean, this is the kind of modern, very refined version. But this has been known since the 30s, 20s, since people started looking at beta decay. You have a beta spectrum. The electron comes out with a spectrum of energies. In fact, the most likely energy for the, so this 18 kilo electron volt is what we calculated on Tuesday, right? But electrons, very few actually come out with the 18 kilo electron volts. Most of them come out with a fraction of the 3 kilo electron volts. And so this is a kind of a crisis because the calculation we did on Tuesday, we didn't assume a lot there. The only thing we really assumed was that whatever this interaction is, energy and momentum must be conserved. And the result we derived on Tuesday, what the result was demanding was that this spectrum of electron energy must be flat and then peak at 18 kilo electron volts. That's the spectrum that our calculation was predicting, and this is the experimental plot. So it's a kind of a crisis, and that's when you're in a scientific crisis, that's the exciting time to live in. That's when you get to propose new ideas and have people test it or whatever. So there are multiple competing proposals. One of them came from Niels Bohr, which I talk about in this thing. One of the proposals of Niels Bohr was he was suggesting maybe energy conservation isn't held strictly in quantum mechanics. And you have to understand this was in the 20s, 30s. People didn't really understand quantum mechanics. Einstein, who got Nobel Prize for photoelectric effect, he never subscribed to Copenhagen interpretation of quantum mechanics. So even Einstein was having difficulty with correctly understanding quantum mechanics. So, and what I will tell you is, skip to the modern times and tell you is that he was wrong. That when Niels Bohr suggests that maybe energy and momentum is not conserved in beta decay, he was just flat out wrong. But it remains that you still have to explain, like if energy and momentum is conserved, like what could we have missed? What could we have missed that what the experimental result we are getting does not agree with our theoretical calculation?
It may release something else.
Yeah, we might have missed something literally. There might be a particle that we could not detect. This was the proposal by Wolfgang Pauli of Pauli exclusion principle. And so what Pauli suggested was we actually literally missed something. So in these outgoing particles, there's one more particle there that we literally missed. So today we call it neutrino. And in fact, I'm being very specific about it. It's actually an antineutrino. Specifically, it's an electron antineutrino. But back then they weren't making this distinction, so let's just call it neutrino for now. It's just a placeholder for a particle that they couldn't see in the 30s, but they were guessing, well, maybe we need to one particle going into two that leads to a prediction that just doesn't hold. So maybe there's one more particle that we are going to call neutrino that's going out. And turns out he's correct. And in fact, there's, even with what little we know, we can actually kind of get at why this is correct. For one, does everyone, so to clear off the kind of big things first, does everyone see that this hypothesis would solve the issue with conserving energy and momentum and still getting this spectrum for electron? Like you can see that? Kind of, you can see if I have 3 particles going out, then now I have enough degree of freedom. I could put all the kinetic energy onto this neutrino, so that electron comes out with 0 energy. Or I could somehow arrange things so that this neutrino comes out with practically 0 kinetic energy. Then, so that I have this, this maximum possible energy that the electron could have in the absence of the neutrino. And so, introducing this neutrino solves that beta decay spectrum problem. And it turns out there's additional problems that this neutrino solves that people in the 20s and 30s didn't know back then. But I think you guys actually have enough information to kind of figure this out with some guidance. So I said all conservation laws must be satisfied at this vertex. But we've been talking about only 2 conservation laws, energy and momentum. We haven't talked at all about the angular momentum. And back then they couldn't because they knew nothing about the spin angular momentum, but we do. So we can consider if we didn't have this neutrino, if a spin angular momentum could be conserved. Yeah? What's the spin angular momentum of the electron? Half, right? It's a spin-half particle. We went over that last week. So electron has a spin of half, let me call it h bar. Does anyone here know so we didn't explicitly talk about it. Does anyone here know the spin of proton? No? Well, you can kind of guess. I call the proton a fermion. So it must be some kind of spin-half. It turns out it's exactly spin-half. And I think back then they actually knew proton was a spin-half based on measurements with the hydrogen atom, because both of them being spin-half makes the hydrogen atom's overall angular momentum to be either 1 or 0. And if you've heard of para-hydrogen and ortho-hydrogen, wait, is that it? I'm not entirely sure. Never mind. So these are spin-half particles. So I guess the excuse for the physicists in the 20s and 30s is that they didn't know much about neutron. So they didn't know the spin of neutron. Well, now we do. Neutron is a fermion. So what do you guess is the spin of neutron? Also half. So these are 3 spin-half particles. So just imagine that we didn't have this neutrino, that this is all the interaction we had. Do you see any issues here? Right? What do you get when you add 2 spin-half particles? I know I said that it was optional last Thursday, but the result of our calculations last Thursday is that with the 2 spin-half particles, you could get spin 0 or you could get spin 1, right? Well, this is neither. So this interaction, unless there's a third particle, doesn't conserve angular momentum. So what addition of neutrino does is it saves angular momentum conservation in this reaction. So once people figured it out, then this neutrino was actually accepted pretty quickly. But so Pauli suggested the idea of neutrino in the 30s, 35 or something. And the neutrino actually wasn't detected in a direct measurement until 1950 something. And but in that intervening 2 decades, people weren't really questioning that this exists because having this neutrino exist solved an additional problem of angular momentum conservation. Question?
Never mind.
Yeah.
I figured it out.
So there are actually some properties of neutrino that we can infer from all the conservation laws that must be satisfied. And that's probably something we should go over, so that maybe that's what your question was, no?
No, my question was why do we detect photons all the time, but we don't detect neutrinos? But then I forgot photons are in the electric field.
Yeah, so it interacts with the charge. So photon, they themselves don't have a charge, but they interact with the charges. Yeah. So let's just list the possible properties of neutrino. So I guess one thing is kind of comes out of this discussion here. What's the spin of a neutrino? Yeah, it's a half spin particle. So It's a spin half particle, which means it's an additional particle we can now add to this list of possibly elementary particles that belongs with the fermions. So, all right, so we have a neutrino here. That's one more particle that we didn't know existed. And back then, in the 30s and 40s, they still haven't detected it. But there's a compelling argument to say that it actually is there. Any other properties of neutrino that it must hold, kind of based on the descriptions, observations? Electrically neutral. It's kind of in the name, but I guess that's circular reasoning. So the reason it's electrically neutral is because somehow we are not seeing it. So if it were electrically charged, then we would have seen it. So that's really the argument for why neutrino must be neutral, because it's sort of like, so it must be electrically neutral. And there's one more thing that's not immediately obvious, but to an experimentalist who's making careful measurements, they could have eventually kind of inferred from their data. And it comes from here. This is where it's a numerical argument. So you kind of have to have trust in the numbers you're working with. So it's the fact that this 18 kilo electron volt is the theoretical number you calculate with no neutrino. And there are electrons with about that much energy. So that means whatever rest energy is in the neutrino must be pretty small. Because if a neutrino had to take up significant rest energy, then you would see this curve come short of this 18 kilo electron volts. So based on that, what they initially guessed was that they were massless. But this is actually a fairly new development in particle physics. The last conclusive evidence was only discovered in 2001. And it turns out it's not massless, but it's, I guess I can say, it's nearly massless. And the kind of experiment that Catherine collaboration does, which is still active collaboration, is they're still trying to determine the mass of neutrino. And there are theoretical reasons why neutrino must be only nearly massless, not exactly massless. But I think we'll skip that, only to show you plot that illustrates what kind of measurement this Catherine collaboration is trying to make. I think I need to scroll down. Okay. So once again, this is all optional. I wouldn't test you anything that's here. That's not also in your assignment. So blah, blah, blah. And so this is what they're trying to measure. And I'm pretty sure this is still plot from Catherine collaboration. That's why they were publishing this at all, because that's what they're trying to measure. So you see that little, so this might still be a two plot, but what they are plotting here now is a kind of different version, hypothetical plots. So this blue curve would be if the neutrino was exactly massless, and this red curve is if the neutrino had a mass of 1 eV. And I think the current upper limit on the electron neutrino mass is 2 eV. So like 1 electron volt out of a energy measurement of 18,000 electron volts. And if this is a possibility, if a neutrino has mass of, I guess, is that 0.3 eV or something like that? So this is in the field of what's called precision measurement. And they are trying to, not so much test, because we kind of know that some flavors of neutrinos that must have mass. They're trying to determine, okay, so what is that much mass for the electron neutrino? So neutrino is the very first of new particles we have to add, because in order to explain beta decay and the features observed in beta decay, we need to hypothesize existence of a new particle. I guess with this particle, this is probably a good place to introduce new conservation laws that that I haven't mentioned at all because there was no chance for this to come up, but this is a good place to mention 3 new conservation laws. So 2 of them are exact conservation laws. Those 2 exact conservation laws are the conservation of what's called baryon number, and I'll explain that. And the second one is similar to this one. It's a conservation of lepton number. And the last one is only an approximate conservation. It's a conservation of what's called, so I think I mentioned this, physicists become more creative in naming things. Baryons and lepton, those are not all that creative. I'll explain why they're not all that creative. This one is, it's a conservation of something called the flavor. And I just have to tell you, it has nothing to do with the flavor. It's like, how are you going to taste the neutrino? But this particular property has been named flavor by the whimsical particle physicists. So I guess how many here know Greek? So these numbers are baryon and lepton. They come from Greek. The etymology is Greek. And what baryon means is a heavy particle. The on is the ending for particles. Baros is, I think, like weight or like heavy, whatever. And lepton, I don't know the actual root word, but it's the light particle. And of these particles, you know the difference between protons and electrons, right? Proton has mass of approximately 1 GeV per c squared, and electron has a mass of approximately 0.5 MeV. Let me use MeV. So proton has a mass of approximately 1,000 MeV per c squared. Electron has mass of approximately 0.5 MeV per c squared. So you see the pretty big gap between these. And in fact, the proton and neutron has a pretty similar mass, not the same, because if they were the same, this wouldn't be possible. So neutron is a little bit heavier, but they have similar mass. So the initial classification that people came up with is that they were calling these as the heavy particles, or baryons. And they called electron a light particle, or a lepton. So with the idea of these 2 conservation laws, let's come back and look at this here. When you look at this interaction or this diagram, is the baryon number conserved? Right? 1 baryon came in, 1 baryon went out. Is the lepton number conserved? Not really, right? I had 0 lepton come in. Before neutrino, I had 1 lepton going out, which is troublesome enough. Even with the neutrino, it looks like I have 2 leptons. So neutrino is a nearly massless or a light particle. So let's say neutrinos are also leptons. But that doesn't really fix my issue. I have an electron going out and I have a neutrino going out. So this is an antineutrino. How many here are familiar with the concept of antiparticles? Not enough of you. So let me just draw the diagram for antineutrino, and I will do a little detour of discussion of antiparticles. So these are the symbols we use to indicate antiparticles. It's for the particle, the typical way to indicate it's an antiparticle, we put a bar over it. So that means it's antineutrino. So this is antineutrino. And in Feynman diagram, we already indicate passage of time from left to right, right? Which means these arrows are actually redundant if all you are trying to say is that that's the direction that the particle is going. So really what these arrows are used for is to indicate, is it a particle or antiparticle? So with a neutrino, it'll be drawn this way. So antiparticle coming into the vertex. So you have a plus 1 lepton number going out, and you have minus 1 lepton number going out for a total lepton number of 0. Yeah? So I guess I need to talk about antiparticles. I want to kind of introduce and finish talking about antiparticles in 5 minutes. And what's the quickest way to do it? How many people here have heard of the phrase positron? Maybe. Positronic brain, science fiction, never mind. So positron is an antiparticle of electron. It was the first antiparticle to be discovered. Let me show you the experimental basis, how positron was originally discovered in the first place. So discovery of positron. There's an iconic image for discovery of positron. So I guess this is probably good. It's from Wikipedia. So this is an iconic image. Wait, where's my iconic image? This is the iconic image for the discovery of positron. You might look at it, what are we talking about? This is, so let me try to kind of describe what's going on here. So one feature I want you to pay attention to is this curved path. You see the curved path, right? Yeah. So it's the curved path. It is the measurement of trajectory of a particle. This is a measurement taken in a device called a bubble chamber or cloud chamber. It's a device used to visualize paths of particles. It actually literally visualize. So now it looks curved. Why do you think it's curved? There's a magnetic field. They put this chamber inside the magnetic field for the explicit purpose of trying to measure the charge of the particle, because what you saw with the alpha, beta, and gamma rays was that was one way of discovering charge of the particle, right? So it's in a magnetic field. And based on the picture, the way the magnetic field is supposed to be set up, I think the magnetic field was set up so that you had a magnetic field that was going into the board. All right. So suppose that you have a particle that bends this way. You have this trajectory of a particle that bends this way. Now, let's suppose I told you that this particle is electron. Then let me ask you this question. What direction is this electron traveling in? Downward, right? Because V cross B, that way goes to the right, but electron is negatively charged, so the force actually points to the left, so that would be consistent with this leftward curve. So if this was an electron, then it would be moving downward. So, okay, so far no discovery. So that's the reason for the placement of this plate here. The purpose of this plate here is to slow down the particle. By slowing down the particle, you can infer what direction the particle was moving. So instead of starting out with what is the particle and then determining its direction of motion, you can look at, well, what direction was it going? And from that, and knowing the magnetic field you set up, infer the charge of the particle. So let me erase all these notations and just have you look at this trajectory with that background information in mind. What's the charge of, what direction is the particle moving? So how do you know it's moving up?
The slope is greater.
Yeah, it curves more quickly here, right? And if you do the calculation, what that corresponds to is that this has less momentum. It's moving slower, that when you go through the calculation, it results in a smaller radius of curvature. So the particle is moving slower than here, which means for that to happen, the particle must have went through the plate this direction, and in the process, it lost some kinetic energy, slowed down. So knowing that direction of velocity, what's the charge of the particle? Positive. So this is the discovery of positron. That's how they discovered the positron. Now, so I'm kind of starting the story from the middle. So obviously this is an apparatus set up explicitly to look for positron, right? Then the question, why were they expecting this new particle, positron, an antiparticle of electron? And I guess I don't really have time to give you the full story. So I will just tell you that this is the kind of quick version of it. These antiparticles, they were predicted by Dirac. That's the name of the scientist, or P.A.M. Dirac. I think P stands for Paul, I'm not sure. Well, P.A.M. Dirac. He's credited with coming up with something called the Dirac equation. It's the relativistic quantum mechanical equation that applies for spin-off particles. And one of the prediction of a Dirac equation is that you need to have a negative energy state. And the way linear algebra works out for relativistic quantum mechanics is you cannot simply say the negative energy states are unphysical. That's not allowed for you. It's kind of for the complete spanning of the space of the solutions, you need to allow negative solutions. So what Dirac suggested was that the universe is filled with what's called Dirac sea of electron states. So there's up to some particular level of energy levels that's filled up with the fermions already. Then due to exclusion principle, those negative states that are allowed in the solution, but the actual negative energy particles cannot exist because it's all already filled up. And then the existing electrons with the positive energy are the states above this Dirac sea ground level. And what he contemplated was excitation of one of those negative energy states into positive energy. Then what you would have is, so okay, I have this Dirac sea that's all filled up. So when you excite one of these filled up states into positive energy state, this is what you would have. You would have a real electron that we are already familiar with, and you would have this hole that's left by the state that was excited up to here. This could happen by a photon being absorbed, for example, and what this hole would get referred to is the positron. And it actually, because it's the absence of a negative energy state, it actually does have positive energy. And so that's where the prediction of the antiparticle comes from. And so it was predicted, people went out looking for it, they found it, antiparticles exist. And I guess the easiest way to think of as antiparticles, it's the same as the particle, except that it has opposite charge. And certain quantum numbers it has, like lepton numbers, are also negative. So that's where this neutrino is, instead of being a neutrino, it's an anti-neutrino. So that's where that comes from. I guess let's leave this there. And as far as the flavor conservation goes, so it turns out there are 3 different kinds of neutrinos. There's one associated with electron, and we are going to eventually introduce 2 more leptons. So far, you know only one. Up to today, we know of 3 different kinds of leptons. So we'll introduce them eventually, but for now, this neutrino that's involved here, it's the one that's coupled together with the electron.
And I think this is the question where it's worth staying for a little bit. It is not a difficult question, but it does involve looking up tables that we don't usually do in a physics class. So for those of you who have taken chemistry class, then this would be a lot easier. But for those of you who might not remember anything from chemistry class or haven't taken chemistry class, so consulting periodic table is really the biggest thing here. That's the thing that kind of requires some level of familiarity. So let me open up periodic table in anticipation of going through this. And as I anticipate answering this here, what I need to keep in mind is how the information is presented here. So the information that they are giving you is in the form of the isotope specification: helium-4, carbon-12, cobalt-60, cesium-137, uranium-235. The name of the element, helium, carbon, cobalt, cesium, uranium, they tell you in a roundabout way how many protons there are. The roundabout way being, you have to know what the atomic number of these elements are. Helium, I think a lot of people might know it has atomic number of 2. It's right here. That's helium. The rest you kind of have to either know or look it up here. Carbon, it has abbreviation C. So C is this one here. It has atomic number 6. So from looking it up in the periodic table, you can figure out carbon-12 has 6 protons. So that's one piece of information. We'll go through all of them. And the number tells you it's the atomic, what do they call it? It's called the mass number. And it's the total of protons and neutrons. So once you know the number of protons and the mass number, then you can get the number of neutrons by subtracting the number of protons from the mass number. So 6. 12 minus 6 is 6. So let me do helium. 4 minus 2 is 2. So that's that. The rest, I actually had to look them up because I'm a physicist, not a chemist. I don't know what atomic number cobalt has. So I do know it's an acronym in the element periodic table. I think it's a CO. So I'm going to look for CO. So cobalt, well, it has to be less than 60. And in fact, usually the stable element isotopes have about equal number of protons and neutrons. So element number of cobalt is going to be close to 30. Yeah, I see someone saying in the chat. Yeah, there it is. So close to 30, but not exactly 30. It's not guaranteed. So 27. So that tells us that it has 27 protons, and 60 minus 27, 33 neutrons. And in fact, the rule I was just telling you, that stable isotopes have about equal number of protons and neutrons, those seem to hold for these two. But you will see that as we go to heavier elements, it kind of starts to skew. Cesium, so if I'm going by the rule I was saying, I would expect its atomic number to be around 68, 69. And I say it in the chat. And, if I'm looking it up at 68, 60 something, it's not here. So, don't spend too much time looking around here. But as you work your way down, you do find it here. Cesium 55. So this is the part where if you're not used to using periodic table, it might take you some time finding the element. Okay, 137 minus 55. That's, I think, 82. At some point, I might use calculator. Could get embarrassing. Okay, uranium-235. No, I see it in the chat saying it's 92. Yeah, okay, there it is. The uranium has the acronym U. Yeah, and the elements around uranium might sound familiar. The thorium and, plutonium has 2 more protons, huh? Somehow I thought plutonium was right above uranium, but I guess it's 2 above uranium. Anyways, so uranium has 92 protons, and you do 235 minus 92, 143 neutrons. And you see that the rule that I was giving you, which was holding well enough here, it starts to shift around here, and around here it's just completely off. Uranium has 50% more neutrons than protons. It's just, I think for this class, we don't spend quite enough time in nuclear reactions for me to make a big point out of it. But there's a fundamental reason for that. There's an actual clear pattern that heavier stable-ish isotopes do have more neutrons than protons. So this question 6 is the one about half-life. It's specifically about carbon-14, which is used for radioactive dating in anthropology and in other contexts. And in the hint, it always kind of tells you to go to the section, and you should if you haven't read the section. And the section describes what half-life is. It's this graph that describes what half-life is. So, so when you have half-life of a radioactive element, in that amount of time, what it means is whatever amount of material you had, in that amount of time, that goes down to half. And here's the interesting thing. In the next amount of half-life, it's not reducing by 500 times 10 to the 3 nuclides. It's actually going half from that. And then it's a half from that. And then it's a half from that. This gives a picture that looks something like what we call exponential decay. And it'll take a very long time for this number to actually go to zero. Well, I mean, in terms of real numbers, it'll never go to zero, but at some point you either have one nuclide or zero. So, so to actually go to zero, it takes a long time, but at any given point in time, if you wait a half-life amount of time, the number of remaining nuclides gets reduced by half. So that's the important thing for you to understand about half-life. And so there are more mathematical ways you can handle this, but this class, I don't know if you are even supposed to know about exponentials. I think for me, exponentials got introduced in a calculus class, so you might not know about exponential, other than one phrase that I don't like very much, exponentially increasing. Sorry, so many people misuse it. I don't like it. But you can do this question in a very intuitive, step-by-step way. So let me demonstrate that. So, it says review, and it gives you the hint of what I'm actually going to demonstrate right now. First, to determine how many half-lives have passed, and use that information to figure out what fraction of original carbon-14 atoms should remain. That's the hint, and that's actually what I'm gonna go through right now. So, let's without further ado, let's get started. So it says, in a sample of carbon containing 1 part per trillion of carbon-14, so 1 part, that's how much carbon-14 I start out with. By the way, the numbers are randomized. You might not get a number that's not 1. That's maybe, I don't know, 0.7, 2, 3, whatever. It asks how much carbon-14 remains after 1719 years. That's a very specific number, but as you're going through this number, you will eventually see that this number of years you are being given, it's going to be in integer units of half-life. So let me just do this. 1719 years. Okay, that's how many years they are. I'm going to divide that into each half-life, 5,730 years. So divide by 5,730. I get 3. So what that means is this particular mathematical relationship is true, that 17,190 is equal to 5,730 times 3. So what that means is this number of years that's given here is 3 half-lives. That's really the information I want. That's half-life is the relevant unit of measure of duration of time in the context of radioactive decay. So here, 3 half-lives. So let me go through this reasoning process. So I'm gonna look at what happens over 3 half-lives. So let me start out with I want different color. So let me start out with 1 part per trillion of carbon-14. After 1 half-life, the question is how many parts per trillion of carbon-14 does it remain? Well, in 1 half-life, half of carbon-14 is going to go away. So, okay, in 1 half-life, this will become 0.5 parts per trillion. All right, that's 1 half-life. So, okay, what happens after another half-life, second half-life? Then only half of that is going to remain. So it's going to be 0.25 parts per trillion that remains. Use a calculator if you have to. And finally, after 3 half-lives, after the third and the last half-life, what remains is half of that. So use a calculator, 0.125 parts per trillion. So that's really all that is. And I give you the integer number of half-life years so that you can go through this reasoning process. If I gave you something that's not exactly 3, 4, 5 half-life, if it's 3.5 half-life, then you have to use more mathematical functions, and that's not what this class is for. So, okay, so after that many years, you have 0.125 parts per trillion of carbon-14 remaining in the sample. Okay. B, carbon-14 is used for a technique called the carbon dating. Oh yeah, I talked about that a little bit. So it says artifact originally had 7 times 10 to the 9 carbon-14 atoms. Never mind how they knew that originally. Let's just say that's kind of subject of the discipline of people who do carbon dating, and they have their methods. And what they are measuring is that the sample has 1.75 times 10 to the 9 carbon-14 atoms. So yeah, okay. So you can read the hint. What I'm going through now is exactly what I say in the hint there. So the first thing I'm gonna do is, okay, how much did the number of carbon atoms did it go down? I feel like the best way to figure that out is to take this original number 7 times 10 to the 9 and divide it by 1.75 times 10 to the 9. 10 to the 9s are going to cancel, so let me just do 7 divided by 1.75. 1.75. So 4. Okay, so what you are getting with this number is that originally there were 4 times as much carbon-14. So how much time would have to pass for the number of carbon-14 to go down by a factor of 4? Well, in one half-life, the amount of carbon-14 will go down by 1 factor of 2. And in the second half-life, it will go down by another factor of 2. So it takes 2 half-lives for the amount of carbon-14 to go down by a total factor of 4. So, okay, so the number of years here should be 2 half-lives. So using the information, 5,730 years is half-life. Let me just do the calculation. 5,730 times 2 for 2 half-lives, 11,460. So 11,460 years old. Submit, and the answers are right. Good.
Hi, I'm recording this lecture video for a couple reasons. I guess let me call this, tentatively, additional particle physics. So right now you should be seeing the page of chapter 14 on LibreText, nuclear and particle physics. I think I mentioned this earlier, that this semester I'm putting together Physics 10 in 30 lectures lecture set. And as I'm doing that, I'm borrowing from my Physics 4 lectures, the bits that are conceptual, the parts that I think will be at the appropriate level for this class. And frankly, I'm doing that mostly because I'm realizing as I start putting together the lecture sets that I didn't have as many lecture videos for Physics 10 as I thought I did. So I'm in the process of doing that right now for chapter 14. And I will say the nuclear physics, which you would have seen as a part of the previous lecture, lecture 28, is more or less complete. So there are these sections that cover it, sections 14.2 through 14.9, 14.10, I guess 14.11, nuclear weapons. And I think the main points have been touched on by the excerpts that I took from Physics 4C lectures, still mostly conceptually. And some of the ones that might not have been covered explicitly were covered as part of the homework help video. There are some calculation questions dealing with the half-life and activity, and I think you saw that as immediate previous section in this lecture set. Now, I'm recording this because as I'm putting together the lecture material that deal with the particle physics, one, the emphasis in the textbook isn't really towards particle physics. There's really only 3 sections. 14.12, the 4 basic forces. 14.13, particles, patterns, and conservation laws. And I guess as a kind of beyond the standard model thing, 14.14, grand unified theories, the unification of forces. So given that relative emphasis, and given that I only have like basically half a lecture, and even if I counted lecture 30, which you will see next week as part of this particle physics lecture, I really only have 1.5 lectures. I couldn't quite put everything that I covered, again, conceptually in Physics 4C into the space that's available for Physics 10. So in this lecture video, I just want you to do a couple things. So I did put some of the particle physics content into what you will see as part of lecture 30. That is our last week's material. Some of it, essay assignment. Some of it just me talking about standard model. And I think having done that, there are some questions in this week's homework set that I haven't quite lectured on. So let me just quickly go through those conceptual questions. And then I want to point you to where you can find additional particle physics content that, again, we don't really have time or space for. But for those of you who are maybe considering physics or astrophysics majors, I think you might be interested in them. So let me show you how to find where that Physics 4C lectures are. They are still mostly conceptual, so I think most of you will still understand it fine. It's just a matter of how much extra time do you want to put in. So let me first do the homework questions. So there aren't that many questions in our last homework set, only 10 questions, and I think only 2 questions involving numbers. And most of those topics are adequately covered in the lectures so far. But in looking through the questions, I saw 2 questions where I do cover the topics, but in lecture 30, which you haven't seen yet. So let me find those 2 questions and I'll just answer and briefly explain them. So they are, let's see here. I think this is the question about the strong nuclear force. I don't think in the lectures I've had the opportunity to talk about strong nuclear force. I'll do that in more detail in lecture 30. So this question says, strong nuclear force binds together constituent parts, protons and neutrons, of atomic nuclei. Choose all statements below which give correct descriptions of the strong nuclear force, and hint will link you to the chapter section. You can always read the textbook. I ask you no questions where you couldn't simply answer them through your knowledge of textbook. So you always have that. Oh, I guess the substructure of nucleus might be considered the particle physics, maybe. So I'll go through each statement, telling you whether it's a true statement or a false statement. So is an inverse square law of force. That's a false statement because an inverse square law of force is a long-range force, like electromagnetic or gravitational force. Nuclear force is quite explicitly a short-range force, both the strong and the weak nuclear force. So is attractive between neutrons and protons? Yeah, probably. Also between neutrons and protons and protons. Is stronger than electric force in the nucleus, right? That's how it overcomes the Coulomb repulsion and binds the nucleons, neutrons and protons together. Is attractive between protons? only part is a wrinkle there. It should be attracted between basically any two nucleons, neutrons and or protons. So this is not true statement. Aids the electric force in holding the nucleus together. No, on this technical basis that electric force is not holding the nucleus together. Electric force is kind of pushing the nucleus apart, especially between proton and proton. So it's not aiding that, it's kind of overcoming the electric force repulsion. Is attracted between neutrons only. Again, the only part is a wrinkle, so I'm not going to select that. And is a short range force. It's the kind of the opposite of is an inverse square law force. One way of modeling the weak nuclear force actually treats it like a contact force. That's kind of the extreme version of a short range force. So this should be correct. Let me submit and see that it's graded as correct. And there was one other question that also dealt with the particle physics content that I really cover next week in lecture 30. So let me go find that. Might be the last question. Yeah, okay, it's the last question. So in particle physics, study of fundamental building blocks of our universe, all particles that make a matter are classified as leptons, mesons, and baryons, whose names were originally chosen according to their masses. Since the early days of particle physics, many new particles have been discovered which fit into this classification structure. For each particle listed below, classify them as a lepton, meson, or baryon. If it does not fit any of these categories, choose force carrier boson, not a matter particle. Oh, so I guess I must be giving you real particles only. And I think in the hint, I'll probably be linking you to section 14.13, which lists all these particles. Let me make sure that it appears formatted correctly. When I was looking at my PDF version of the textbook, the tables appeared kind of messed up. So yeah, so I think you have to be in the right zoom. Yeah. So if table 14.13.1, if it appears messed up, just to zoom out until, it looks reasonable. So I think I'm gonna be at 90% zoom for that. So so let me do it this way. I'm gonna first answer all the parts here from memory, and then I'll point you to in the parts of the table where you could find the information. So now the omega particle is part of the lecture that I had to cut out. I will show you where you can find the lecture that I cut out, but it is a baryon. It's a baryon with a strangeness of -3. It's a very rare particle. There's a whole history of the quark model that ties into this. Electron is a lepton. I think I talked about that already. Photon is a force carrier boson. It's the light particle. It's the mediator boson for electromagnetic force. Sigma, if I remember that correctly, that should be a baryon. I think it has some strangeness. Gluon is a force carrier boson. It mediates the strong force. Muon is a lepton. It's the second lightest or second heaviest lepton. I guess charged lepton, because there's whole neutrino business. Muon is a lepton. It's not a meson. Neutrino is a lepton. All three flavors of it: electron neutrino, muon neutrino, and tau neutrino. So it's a lepton. Kaon, this is one of the strange mesons. So this should be meson. There's like 4 different versions of it. 2 charged, 2 neutral. Pion is a meson. This is the lightest meson. It comes in 3 varieties. 2 charged ones and 1 neutral one. Neutron is a baryon. It's on the other side of proton. Oh, and proton is a baryon. Yeah. So those are all the answers. Let me match them up to the table in case, you don't have them memorized the way I do. So this is the table. So I think I can match them up. Omega here is under the hadrons. Oh, let's see. Hadrons are here, omega. The particle version of it is omega minus. It has charge of -1. It's a little heavy, not that heavy. Electron, because I don't really need to find it here, but electron is here under leptons. Photon would be force carrier or gauge boson. Sigma is a baryon. Baryon is a hadron, but hadron can be meson too. Sigma is here. It comes in different varieties, different charges. I think they all have one strange quark in them. And gluon is a boson. Let's see. Gluon's not listed here. Interesting. I wonder why it's not listed here. Gluon. Okay, it's missing from the table for some reason. It really should have been listed under either gauge or just a boson. Sorry. It's the strong force carrier. Muon is here. It's one of the leptons. Neutrino is here, again, one of the leptons, and they're listing the electron neutrino, and the 7 eV, that's not the actual mass. That's probably the upper limit that's a little bit outdated. I think the most recent upper limit is like less than half eV. Kaon, or K meson, is these. These are the 4 kinds, the positively charged, negatively charged, and the 2 different kinds of neutral K meson. Unlike the neutral pi meson, neutral K meson is not its own antiparticle. There are 2 different versions. So pion is a meson, and neutron is a baryon, and proton is another baryon. It's the lightest baryon, actually. It's the only stable baryon. Neutron, a free neutron, would be unstable because it can decay into proton and electron. And neutrino. Technically anti-neutrino. All right, let me submit this. And those are the 2 questions that requires some particle physics topics that I haven't yet covered in lectures. If you're interested in the details, some of this I'll talk about in lecture 30, so you can look for that next week. Now, for those of you who are interested in more particle physics content, the next 5 minutes or so is for you. Because what I would tell you is that the particle physics related lecture I gave for physics 4C, nearly all of that is suitable for you as well. At that later part of the physics 4C, all of that is kind of covered conceptually, not involving any advanced math. So let me show you how you can find those lectures. So you can find them on YouTube. If you search for COA physics, I'm logged into the account right now, but if you search for COA physics, you should be able to find our channel. It also has a pretty short handle, at COA physics. That's our handle. So within the channel page, on the front page, there's these, physics in 30 lectures. Physics 10 in 30 lectures, almost done. I have 27 here, I think. Physics 4A, Physics 4B, and Physics 4C in 30 lectures. And, most of Physics 4C, it's the 3rd semester of engineering physics. It does have fairly high math prerequisites, but you can skip all that. And the special relativity content that's here, that can be a bit mathematical. Now you will recognize the conceptual pieces that I have borrowed for your lecture. You would have seen them earlier. Same thing in the quantum mechanics. You have seen the conceptual pieces. Now, this is what I would tell you. After we finish covering special relativity and quantum mechanics, starting with around lecture 25 or so, it's quite conceptual. Even atomic physics, it's more about the quantum numbers and periodic table. And spin angular momentum is mathematical in that it involves linear algebra. But once you start on lecture 27 and on, it's all conceptual. So lecture 27, you wouldn't see anything new. I think I included almost everything here into your lectures. And lectures 28, 29, 30, that's where, because I had to fit 3 lectures worth of material into 1.5 lectures, I've cut out quite a few. So if you are interested in additional particle physics content, this is where I would say watch these 3 lectures, lecture 28, 29, and 30. I'll just highlight some topics that I have skipped. So I guess I can talk about it using the table of contents here. So let me just get to the table of content. So the parts that I've skipped, so I had to skip intro to Feynman diagrams, mainly on the basis that we don't do much with it. And the illustration of Feynman diagram rules with examples, had to skip that. I think you have in your lectures early particle physics, discovery of neutrino, that is part of lecture 29, and more conservation laws and antiparticles. I think that's all I could cover in lecture 29. So you have half of this. So if you are interested in Feynman diagrams, watch the first half that I had to cut out. And in lecture 29, this is the table of content. And so half of it you will see in lecture 30. Nuclear forces and Yukawa meson, search for Yukawa meson. You will see that in your lecture 30. That's the, I guess, the middle third of it. Discovery of so this is the discussion of strange particles, starting with the K meson, conservation of strangeness, and an organizing scheme for that called eightfold wave, developed by Gell-Mann, and discovery of the omega particle. It's this history that I had to cut out of your lectures. I would have loved to include these, but I couldn't find the space for it anywhere without adding an additional lecture or something. So that's why I'm recording this now, to tell those of you who may be interested that you can find them here. The first half, you already have it in your lecture 30, so you will see them. But the rest of it, the second half, if you wanted to hear that somewhere, then you can find it in this lecture video as lecture 29 for Physics 4C. Okay, let's look at lecture 30. So in lecture 30, we have intro to quark model. Yeah, I think I had to skip that. And I also had to skip the discussion of the weak interaction elementary vertexes, which tie into Feynman diagrams anyway. And the weak interaction example, I think this has Feynman diagrams in it too. So yeah, I had to skip out on those. So what is included in your lecture 30 is this last third, the standard model. There's one bit that I had to edit out for, again, time. I had to edit out discussion of what's called asymptotic freedom. So if you want to see that, you can watch this version here. There's a version talking about asymptotic freedom. I want to say maybe somewhere around, yeah, I think somewhere around here. There's a question about measuring mass of the up and down quarks, and then I have about 3-4 minute answer talking about asymptotic freedom and the deep inelastic scattering. So yeah, that's the bit that's missing in your lectures. So I'm recording this now to show you where to find them for those of you who are interested. It's not quite required material for you. Even lecture 30 is, mostly optional. So I mean, the content I cover in lecture 30, you don't really have to know it to complete the remainder of the assignments and all that. But for those of you who are interested, here's where they are. So I hope you find it useful, and if there are any questions, please let me know. This is the end of the semester, and other than answering your questions, I don't really have a lot to do. So any questions, please let me know. Thank you. Bye.